As we continue our discussions on applying derivatives into the applications of the world, we're going to focus in on some business applications as well as in ways to optimize situations. So when we talk about the word optimization, we're talking about how do we make the situation the best possible, and it depends on what you're talking about. If your goal is to have the biggest yard for your dog, then you are trying to optimize perhaps the area of your yard, even though you'll have some limitations on the amount of fence that you can put up. Or you might want to minimize your cost, and so optimization takes on different meanings based on what the situation is. First, let's take a look at a typical profit and cost graph. So the black line that we have here is our revenue. This is the money that we have coming in, often called R of X. Okay, so that's our money coming in. And then the red line is our cost, and often called C of X, and that is our negative money. What's the money going out? And when we talk about profit, then our profit is when we take our revenue, the money coming in, and we subtract our costs. Now let's talk about this graph a little bit. At first, at the beginning of our company, if we're opening our company's doors, if we notice, the cost graph is higher than the revenue graph. And so the problem here is that our cost is greater than our revenue. And so if we were to subtract our revenue minus our costs, our profit would be negative because our cost is more than our revenue. If we go to this point right here where the two graphs meet, this is where our revenue equals our cost, and perhaps you know what that might be called. That is called our break-even point. That is when our profit equals 0. So the good news is we're not losing money. The bad news is we're not making. But that might lead to a reverse in the graph, which puts our revenue so now we have our revenue is greater than our cost line, and therefore we're going to have a positive profit. So when the revenue is greater than the cost, we have a greater profit. Looks like something's happening in our company, that we hit a break-even point again, where the revenue equals our cost. So that's a break-even point, and our profit equals 0. And unfortunately, we have gone back into having higher cost here. So the cost is greater than the revenue. We are back into negative profit. Now there are good reasons why that might happen. This break-even point right here might represent the point where the company cannot build any more under their current conditions. For example, if I manufacture cars, my factory can only handle making so many cars, even if I run it 24 hours a day, 7 days a week. I might be able to manufacture 100 cars a day at that location. But the market wants me to make 200 cars a day. Well, if I decide to venture there, then what happens is I've got new startup costs. I've got to buy another building, I have to buy more equipment, and so for a while my cost will exceed my revenue. Another question that we like to talk about when it comes to looking at this graph is, at what point is our profit or our loss the greatest? And if you look kind of where I'm drawing these vertical lines, but you can kind of see that where those two graphs, the red and the black graphs, are farthest apart is where your greatest profit or loss would be. So the profit or the loss, the positive or the negative profit, is greatest when your cost and revenue are farthest apart. Well, when does that occur? Well, let's take a look. And my drawing's not perfect, but if I were to draw this blue line right here, and let's talk about the slope of that blue line. Remember, the slope of a cost function is really its first derivative. And if you think back to early in the semester, we talked about something called marginal cost. Marginal cost is how much change is there if I increase my production by 1. So if I up my production 1, will my cost go up or down? Well, you can see that in this case, the marginal cost is very little, so it would probably benefit us to do that. And if I draw down here, the tangent to the revenue function, that would be our first derivative of the revenue, or also our marginal revenue. If I go up here and do the same thing and draw the tangent to the revenue there and the tangent to the cost there, what you might start, oops, that's my revenue. What you might start to notice is that these blue segments look pretty parallel. And that is the case that the maximum profit or loss always occurs where the marginal revenue equals the marginal cost. So when the cost and the revenue are both changing at the same rate, we will experience the greater profit or loss. So when our first derivative of revenue equals our first derivative of cost, we will experience the greatest loss or profit. So companies look at these types of graphs all the time to make sure that they are keeping an eye on whether their cost is overtaking their revenue, whether their revenue is overtaking the cost. And likewise, they are looking at those break-even points because that's when there would be significant change in their company. Let's put some of this to use. So we're going to be using a couple of things. Remembering that maximum profit is where the revenue, the change in revenue equals the change in cost, and also that profit equals revenue minus cost. All right, so let's take a look at making some business decisions here. A manufacturer can sell X items a week for a revenue given by R of X. The cost of this item is given by C of X. What is the most profitable number to make each week? Some of us would like to think that all we should do is make the most that we can, but in fact it is sometimes better for your company to make fewer items or more items. One company, if you ever want to go look at some business reports regarding the Wii never made enough consoles for many years of its when it first opened. It wanted there to be a shortage on the market, and that made them most profitable. They had one of the best business plans that I've ever seen. So let's take a look at this. We have that a manufacturer can sell and bring in a certain revenue. We have the cost. What's the most profitable? That is when we want our change in revenue to equal our change in cost. So the first thing we're going to do is take the derivative of our revenue, which is 200 minus 0.02x. We're going to take the derivative of our cost, which is 50. Now take a second and solve that for x. So negative 0.02x equals negative 150. And so x equals 7,500. So if we take the if we're manufacturing, I don't know what, bicycles, what this says is that based on our revenue and our costs, that we should produce 7,500 items, bicycles, whatever, per week. If we go over that, our cost will start to overtake our revenue. It doesn't mean we won't still make a profit, but it's just that it will start to overtake it and eventually eat away at it. Right? Next, we want to minimize the average unit cost. We want to minimize the average unit cost. So think about back to when we maximized and minimized things. The maximum or minimum value occurs when the first derivative equals 0, because remember that's when we have a turning point, and then we would need to check our second derivative to see if it's positive or negative for concave up or concave down. Now, we're not going to just take the derivative of c of x, because c of x is the cost. We want to minimize the average cost. So first we have to come up with an average cost function. And to find your average cost, you take your total cost and you divide it by however many items you are making. Well, our total cost is given by the function x cubed minus 6x squared plus 15x, and we are making x items. So our average cost function would just be x squared minus 6x plus 15. Now we take the first derivative of our average cost, which is 2x minus 6. We set it equal to 0. So 2x equals 6, x equals 3. And now we need to verify that x equals 3 would be the number of units that would minimize the average cost. And to do that, we would take the second derivative, which is 2, which is positive, which means our area is concave up, which means that point is a minimum. So at the production of 3 units, okay, you reach the minimum average cost, and the minimum average cost, I'm just abbreviating there, is a dollar amount. And to find that, we simply have to plug 3 right into there. So we get 9 minus 18 plus 15. So we get negative 9 plus 15, so we get 6. So there would be an average cost of $6 a unit if we make 3 units, and that is the lowest number of, or that's the lowest average cost we can experience. Okay, so make 3 units and you're going to spend the least amount on each unit. Now notice we haven't said the word profit because we're not talking about profit here. It may be that we want to spend more because maybe our profit will be higher if we make 4 items. So this is just talking about cost in this example. The next thing I want to talk about is actually one of my favorite because it is so applicable in everything we do. Have you ever ordered anything? You've ordered a batch of t-shirts for an organization and you ordered 20 of them and you got them for a pretty good price, and then you realized you really needed 21 and you went back the next week and said, okay, I need 1 t-shirt, and you ended up paying boatloads more money for that 1 t-shirt than you did for the individual t-shirts in the batch of 20. And that's because there's some economy of batch sizes. Think about that company that's making the t-shirt. When you ask them to make one or ask them to make 50, there are certain things that they're going to have to do no matter what. They're going to have to ink the screen printing press. They're going to have to clean that after they're done. So whether they make one shirt or 20 shirts, they have to ink it and they have to clean it, and that costs time and money. To ink a machine, you waste ink because it takes a while for the ink to saturate the press. So if you're only doing that for one shirt, you're wasting that same amount of ink for the one shirt that they did with the batch of 20. So we can look at what is economical both in terms of placing orders and also in terms of producing. So what if if I knew I was going to make 50 cars this year? Would it be better for me to make all of those cars all at once, or would it be better for me to take those cars and make one a week? And again, what's the economy of that? So look at this example. We're going to talk about that we know that we have a market for 1,000 tricycles a year. So what we're talking about first is I am the producer. I'm the company that's making the tricycles. I know the toy stores are going to order 1,000 a year. I need to decide whether I make them all at once, or whether I make 2 batches of 500 or 10 batches of 100, or what. Now there are some factors in our decision. Q will call the quantity in each batch. So will I do 1,000, 500, or 100? K is the cost of storing per unit per year. Okay, the cost of storing per unit per year. F is the fixed setup cost. In the example of my t-shirts, F is the amount that it's going to cost me to ink the press and clean the press, because I have to do that no matter how many t-shirts I make. G is the cost of making one unit. Now this is a fixed cost. It is not incorporating the setup cost. If you only do that one t-shirt, whoever buys that t-shirt has to pay all the setup cost. But they're really only paying a certain amount for the shirt itself, and then they're paying all that setup cost. So whether it costs us to make whether it costs $3 for that t-shirt or not is kind of what we're talking about G here. And M is the total production. So using that, let's talk about what is in our total cost. When we figure out our total cost, we have to figure in two things: manufacturing and storage. Okay. Manufacturing has to do with the number of batches you're doing. So I'm going to jump up here because I'm going to show you a trail. So total cost was manufacturing plus storage. Manufacturing has to do with the number of batches you're doing and the cost for each batch. And storage is storage. Okay. Well, let's talk about the cost per batch. So number of batches, the cost per batch has to do with both the fixed cost plus the cost of producing each item. And this is how a company would build a function like this. So now let's take that and let's plug in some of our variables. The number of batches that we're doing would be how much we need total. So how many t-shirts do we need total, and how many are we putting in each batch? So the number of batches would be the total production. We need 1,000 tricycles divided by how much we're putting in each batch. Our fixed cost we called F. Our cost per item would be and when we say cost per item here, we're looking at total cost per item because we're making a bunch of them, right? So we're making a certain quantity and each of them cost a certain amount. So it's cost per item total because we're trying to find total cost. The storage is a little bit weird, and I'll try to explain it, but I'm not going to spend a lot of time on it. Is this. K is the cost of storing 1 unit per year. The cost of storing 1 unit for 1 year. But we're not going to store all of our units for a year. So what the model is that's used is you take the quantity that you're making in each batch and you divide it by 2. With the idea being that you are, in the end, even though you might store some items up front, when those items are gone, other items can fill their spot. And so in fact, you don't need storage space for 1,000 because you are not producing all 1,000 at once. And so you can kind of share that space. I know that's not a great explanation. It's a little confusing, but I do encourage you to read about it a little bit in your book on how they justify that dividing by 2 is you only need half the storage spaces for your total quantity because you're not storing them all for the whole year. So that represents our total manufacturing. Now remember that we are trying to optimize something, and so we are trying to optimize our total cost based on the choice we make on our quantity per batch. So we're trying to optimize or minimize our total cost based on the quantity we pick for each batch. Okay, so that's what we're trying to determine. How many should we make in each batch in order for us to have the lowest total costs? Now it's really cool how this works out. It's very messy, but I would encourage you to give it a shot if you like doing derivatives. We take this function that we just had on the last screen, and I'm just distributing the m over q here. So fm over q. So that parentheses I had, I distributed it because that cleans it up just a little bit. And make sure to keep your G's and Q's straight. Now, what's important to realize here is what are constants. Okay, so what is not changing. And so F is a constant. It's the fixed cost. It's the fixed setup cost. It's not changing. M is a constant because it's our total production for the year. G is a constant. If we say that it cost us $3 to make a t-shirt. Now somebody would argue, but if you make more it might cost you less. And you're exactly right. What you could choose to do as a company, for example, is to use your average cost as your G, that type of thing. We said M was a constant, and K is a constant because that's our storing cost. So the only thing that is not a constant are the Q's, and that is what we will be taking the derivative. To find our derivative of our total cost, okay, we're going to take that in respect to Q. So that's just Q to the -1 and a Q down there. These are pretty basic derivatives. Remember, F and M are constants. So we end up with this, and again I encourage you to try this to see if you get the same thing. The derivative of that is 0 because all of that is a constant, and we end up with that. And then next, set that equal to 0 and solve for Q. So take this right here, set it equal to 0 and solve for Q. And when you do, you should get this. So I really do encourage you to give that a shot, just a little bit of algebra. And that is the formula for finding the most economical batch size. We are, though, assuming that the demand is constant. In other words, I know I will need 1,000 tricycles. Halfway through the year, they're not going to change their order on me. So I have guaranteed for 1,000 tricycles. And we talked a little bit about why G doesn't play into the formula, and that is because we are using either the cost, the constant cost, or the average cost that has us average cost or constant cost that is not going to change no matter how many we put in each batch. In other words, those tricycles I'm selling cost me the same for the parts. I'm not getting a discount for huge quantities, or if you are, you could put the average cost in there. Let's put this to use. So we have a manufacturer who can make 16,800 cases of sugar. It costs $3 to store one case for 1 year, and it costs $7 to produce each, not batch, but each item. It also cost me $200 to set up for production. So let's identify our variables. So remember, Q is what we're trying to find out, is how many we're going to put per batch. K is our storage cost, which is our $3 per unit per year. F is our fixed cost, and that is our setup cost, so that's our 200. G is the cost per unit, and that was $7. And M is our total production needs, which is 16,800. And so now we plug into the formula, square root of 2f, oops, that's a lowercase, fm over k. So notice some of our numbers aren't coming into play. So just because they're in the problem doesn't mean you use them. And when you work that out, you should get 1496.6 items per batch. Now, some would argue that you can't make 0.6 items, and in some cases you can, in some cases you can't, in some cases you could carry them over to the next day. What you would do is analyze 1496, you could do a bunch of batches at 1496, and then you would have one more batch with a little extra. And the companies would just look to see which one was clearer. Now we need 16,800, and we're making 1496.6 per batch. That means we're going to have to do 11.2 batches, which we would say we need 12 batches. Now be careful on Math Excel because they may want the 11.2. Click on View an Example to see how they want those answers put in. So it's a simple formula that comes from calculus. I guarantee there are people out there that use this formula that didn't know they were doing calculus, and I guess really they're not. But where that formula came from has to do with calculus. And if your company had a different total cost model, you could create a different formula for your company by setting up your total cost model, taking the derivative of it with respect to the quantity per batch, and then you would have your own formula. But this is a pretty basic generic formula that works in a lot of cases. Now let's turn the tables. And now you're the little guy. You're placing the order for the bikes. And your store is going to order 500 bikes total. And the question is, do you order them all at once or do you order them in smaller batches? The formula is the same, but the variables take on a little bit different meaning, so let's take a look. Q is still the number per ordered per batch. So this is the number per order. So you ordered that t-shirt, you ordered those 20 t-shirts, and then you had to go back and order one more. So you ordered one batch of 20 and one batch of 1, and was that most economical? You are still going to have storage cost. Because if you order 500 bikes, you're not going to sell 500 bikes all in the same week. So you have a storage cost, and that storage cost then will affect whether it's going to eat away at your profit if you're having to pay for storage. You have a fixed cost. You've heard of it. Maybe you're not thinking about it as a fixed cost, but have you ever heard of shipping and handling? Have you ever asked what the word handling meant? What is it they're charging you for? And so whether you order 1 item or 50 items, you pay a $10 handling fee for that order. And that's what killed you on that 1 t-shirt order. So the 20 t-shirts shared that handling cost. The 1 t-shirt didn't. And M is still the total that you need. Now, again, to develop this formula yourself, and it goes the same way, the total cost is your storage cost plus your reorder cost. Okay. And so your storage is your, and I got those in the wrong order, but that's okay. So storage, your reorder cost is the cost to order. And you might only order once, so reorder, maybe the RE isn't needed, plus the number of orders. That's really what's going to make a difference here. Okay. You're still going to be paying for the item. So the cost of the item doesn't play into this at all because you're going to pay that whether you order them all at once or not. Now certainly if you get a discount for ordering in bulk, you have to create that model and take a look at it differently. When you plug in for this, your storage is still the K Q over 2, and then your cost to reorder is your F, and the number of orders would be your total divided by the size of the batch. And when you take the derivative of that, you get the same exact formula, which is the 2FM over K. So I encourage you to play with that to see how those formulas develop, because companies would develop their own models as well. So here we're trying to determine what's the best size of order to minimize the cost. Okay. And we talked about how that was developed in that you find the derivative of your total cost function, set it equal to 0, solve for Q. And so the formula is the same. You just have to think about the variables a little bit differently. Here we're just assuming the demand is constant, that if I know I can sell 500 tricycles this year, so I'm not going to get stuck with them at the end. What happens to some companies is they think, oh great, I can buy 1,000 of these widgets, and then they only sell 300 widgets. So it's understanding that the demand is constant. And again, G is the cost per item, that's not changing, but if you got the bulk discount, then that would play into making things play a little different, and you would probably want to use average cost. So let's take a look at the bookstore. The bookstore knows that if they order the best-selling cookbook, they can sell 100,000 of them. It costs 50 cents to store it, and it costs $60 every time they place an order. So let's identify our variables. Q is the number per order, and that's what we're trying to figure out. K is our storage, which is the 50 cents per unit per year. F is our fixed cost per order, which is $60. and M is our total need, which is 100,000. So we put in Q, 2 times F times M divided by the storage. And we find that we get 4898.7 books per order. And so we would probably go ahead and order 4899 books per order. And if we have a total need of 100,000, that gives us 20 full orders, but we need an extra partial order, so 21 total orders is what we would end up placing. And so companies, I have a friend that works with the Omega Protein fish oil factory, and they have to decide what to produce and how much storage they have, and that storage has a big cost with it because it has to be kept at a certain temperature. So do they build more storage, produce more items, sell them later, or do they sell them up front, that type of thing? So all different types of companies deal with the idea of ordering or producing in batches and what is most economical. So hopefully you'll have an opportunity to use this concept as you venture out into different careers. So two different things. Remember that the best profit is when the marginal revenue equals the marginal cost. That optimization is when the first derivative equals 0. And that the batch order formula works for both the consumer and the producer.